So, it is my great pleasure to introduce my friend and colleague John Wilson, who's going to be telling us about one of the best searches and studies that is still going on at Fermilab. Now, Fermilab stopped taking data a while ago, but it is still the only data at the high energy frontier of proton-antiproton, which is very different than the LHC proton-proton. So your one is able to do very different things. And as we go through the end game of that data, there are certain things which don't make sense and which very much could be evidence of new physics, but it's hard to tell. So one has to really go through and dot the I's and cross the T's, and John has spent his the last many years really doing that. It's a really impressive piece of work that the LHC is not going to be able to do. So this is an exciting thing that we get to see. John is an old friend. John is originally from Texas. He grew up in Richardson, which is just north of Dallas. He then had the, let's call it, choice of going to Baylor for his undergraduate work, where there's actually a fairly strong CDF group with a bunch of friends of R.J. Dittman is there, and some other folks who are currently CMS colleagues. He then went to join some friends at Ohio State, where he did his PhD work, again on CDF, where he was working on Higgs physics and top physics. And then he was recruited to the University of Michigan, where he was a postdoc, where he's been doing top physics for a number of years, being a leader, especially in the top quark production and asymmetry, but is also the co-leader of the top quark, the combined top quark, beyond the standard model searches, and Higgs physics, all in one giant group. So John's breadth is really quite large. And in the near future, and essentially in January, we have been able to steal him to come here to A&M, where he's going to become a research scientist on the CDMS experiment. So we're very excited to have John here today for his first visit to A&M to tell us about these anomalies in the asymmetry in TT bar. So please join me in welcoming John to give this talk.
Thank you for that introduction, Dave. That was very nice. So I've got just a few introductory slides that I'll go through fairly quickly, I think. Of course, we know we have the standard model. It describes pretty much everything that we know anything about. There's the three generations of fermions, the quarks, the leptons, the neutrinos, and the interactions among them mediated by the vector bosons. Also the Higgs scalar that was recently discovered at the LHC. Now today I'm going to mostly tell you about the top quark. Okay, so the top quark is the third generation up-type quark. It's very massive. In fact, it's the most massive fundamental particle that we have ever seen. This one fundamental particle has about the same mass as an entire molecule of caffeine. And so this large mass means that the Yukawa coupling between the top and the Higgs is fairly close to 1, which may mean that we're in some kind of a non-perturbative region, which may in turn indicate that top studies may be a good gateway to understanding or discovering new physics. So it's a very good thing to study. Top quarks are mostly produced like any matter particle in particle-antiparticle pairs. They can be produced singly, but that's a relatively low rate and not the subject of this talk. So the top pairs at a hadron collider, which is the only place we've been able to produce them, are produced from a quark-antiquark or a gluon-gluon initial state. And at leading order, this proceeds principally through an S-channel diagram with a gluon in the S-channel like this. Now once you go to next to leading order, of course you get one-loop diagrams and you get radiation diagrams. So you get particularly this gluon-box diagram, and those start to come into play. And then also in all of these diagrams, you can take out the gluon line and replace it with a weak boson or a photon. And that produces some small contribution to the total cross-section and some small alteration to the shape of any differential cross-section. Okay, so now what is this forward-backward asymmetry, AFB, right? Well, it's a property of top pair production. So you look at the momentum of the top, and you look at the momentum of the antitop, wherever they came out of the interaction, and then you see, you also look at the direction of the momentum of the incoming proton, and you see which of the top and the antitop is closer to the proton direction. And if the top is closer to the proton, you call that a forward event. If the antitop is closer to the proton, you call that a backward event. So you count the number of forward events, and you count the number of backward events, and you take the difference and divide by the sum, this quantity that ranges from -1 to 1. This is the forward-backward asymmetry, AFB. Now, in the standard model, at leading order, where you only have that single S-channel diagram, the asymmetry should be 0, identically 0. When you go to next to leading order, you get interference, between the initial and final state radiation diagrams, and you get interference between the box diagram and the S-channel diagram. And so you get a modest asymmetry of about 6.6%. And interestingly, this asymmetry actually winds up being very closely tied to considerations of parity and angular momentum, although the details of that wind up being really outside the scope of this talk.
Is that 2% in that number actually included the next to next leading order?
There is not yet a next to next leading order calculation. There's one in progress, but this includes most saliently scale variations. Okay, so now we know how we make top quarks and what we want to know about them. How do we actually see them? Well, of course, quarks are not free particles. You only get quarks as part of hadrons. And so when you produce a high-energy quark in a collision, it hadronizes and you get instead a spray of hadrons called a jet. Top quarks, though, are special. They're heavy enough that they decay to a W boson and a bottom quark before they form a jet. And so this feature allows us to identify them and reconstruct them. The bottom quark will then, of course, being a quark, form a jet. And then we have the decays of the W boson. So we can split top pair studies up into several different categories based on the decays of the Ws. If both W's decay to a lepton and a neutrino, then that's the dilepton final state. If one goes to a lepton and neutrino and the other one goes to two quarks, lepton plus jets, and of course all hadronic where they're both quarks. Okay, so now we know the basics of top phenomenology at a very high level. How do we actually do this experimentally? So we have to have a high energy collider like the Tevatron, which was a proton-antiproton collider with a center of mass energy of nearly 2 TeV. We ran for 10 years and collected about 10 inverse femtobarns of integrated luminosity at two different particle detectors, CDF and D0. So they're very similar. I'll tell you very briefly about CDF. It's a general purpose particle detector, nearly covers the entire solid angle. It's very large, very heavy. In the center, there's a very large and high precision charged particle tracker that's inside of a solenoidal magnetic field, coaxial with the beamline. And then outside of that, you have calorimeters, and then outside of that, you have muon detectors. So of course, charged particles, electrons, muons, and charged hadrons are all going to leave tracks in the tracking system, and the curvature of the tracks in the magnetic field gives us the momentum. Electrons and photons are going to leave all of their energy in the electromagnetic portion of the calorimeter, hadrons in the hadronic calorimeter, and when we stop everything else except for muons with some steel shielding, so if we see any signal in the muon chambers, it's probably a muon. And then finally, neutrinos. Well, we can't see neutrinos at all in this detector, so we have to infer their presence from an imbalance in the momentum in the whole event. Okay, now I talked about jets and I talked about hadrons. Well, of course, our calorimeter is unfortunately too coarse to resolve individual hadrons, but we don't really care about our individual hadrons. So we run a jet finding algorithm, which just looks for a cluster of energy in a small space in the calorimeter, and that tells us where the jets are. Now, bottom quarks are actually kind of special because the B mesons that you form as part of the jet will actually travel up to about ½ centimeter before they decay. And so your jet winds up having, if you take all the tracks that are part of the jet and extrapolate them backwards, you find that there are two different points that the tracks converge to, two different vertices. And so a very high precision silicon tracker allows us to identify those and identify which jets are B jets and which are not. And so this is very crucial for top studies because you always have the two B quarks in the final state. Okay, now that we've got all of the final state objects from top decay, how do we actually get the top and the antitop? Because remember, we need the top momentum and the antitop momentum in order to study the asymmetry. Well, we know that there's two W bosons and two top quarks, so we just try all the different combinatorics of how you match the jets to the quarks, etc., and we can make a chi-squared that matches the reconstructed W's to the W mass and the reconstructed tops to the top mass. We minimize that chi-squared and choose the best matching between jets and quarks. And finally, we have our T and T bar 4 vectors. So that's basically how we're going to do these analyses. So now let's actually talk about one of the analyses. So I'll start by talking about the CDF analysis and the lepton plus jets channel. So of course, we're trying to get a very pure sample of TT bar. So we require a high momentum lepton, either an electron or a muon. We have a large momentum imbalance, we call missing transverse energy, that indicates a neutrino. And we have at least 4 high energy jets, the 2 B jets and the 2 jets from the other W. And we require at least one of the jets to be B-tagged. This gives us a sample that's about 75% TT bar with a large enough sample size that we can actually do something with it. The remaining events, the other 25%, come variously from a wide variety of backgrounds, mainly W plus jets productions and QCD multi-jet production, where one of the jets is incorrectly reconstructed as a lepton. And then we estimate our backgrounds from a combination of Monte Carlo simulation and data that we select from top signal depleted sidebands. Okay, so then we take our reconstructed top and anti-top 4 vectors. Oh, and I should mention we identify which one is top and which one is anti-top based quite simply on the charge of the lepton, which is an exact determiner of the top and the anti-top. So then we compute the rapidity of the top and the rapidity of the anti-top, and we take the difference, y of the top minus y of the t-bar. And when this is greater than 0, then that means, when that difference is greater than 0, then that means that the top was closer to the proton, and that's a forward event. When it's less than 0, then it's a backwards event. And you can see, once we plot the spectrum of this, that the points on the right are above the prediction, the points on the left are below the prediction. That is the asymmetry. You can see it right there. And if we count the number here and we count the number here, take the difference and divide by the sum, this is an asymmetry of 6.3%. Now you'll say, oh, well, that's perfectly in line with the standard model of 6.6%, right? We're done. Well, okay, not quite yet, because at this level, we're still worried about the fact that we have some top pair events that go undetected. We have the effects of our backgrounds, and of course, sometimes we just fail to properly reconstruct the top and the anti-top 4 vectors. So we have to correct for those effects before we can really compare directly to simple theory calculations, or before we can compare to results from other experiments. So we do this, handling the backgrounds is easy. We already have the background shapes, so we just subtract those away from the data. And then we take a sample of fully simulated Monte Carlo events that are a TT-bar simulation, and we run our analysis software on those. So then we have the original generated top and anti-top 4 vectors, and we have the reconstructed top and anti-top 4 vectors. From that, we can build up a matrix that describes the response of our detector, both in terms of selecting the events that are there or missing them, and also in terms of the resolution and smearing of the detector. And then we can invert this matrix and multiply it by the data, and that takes care of correcting for everything. Well, almost. There's a problem, which is that this matrix accidentally or perhaps universally is very close to a singular matrix. And so if you try to invert a matrix that is numerically close to a singular matrix, you get horrible, horrible numerical instabilities. And so we're able to tame this by adding a regularization term. And the particular technique that we use to do this is singular value decomposition regularization in a paper by Hooker and Karpelish-Blue. And so once we've done that, then we get a result at the parton level of an asymmetry of 16.4% with an uncertainty of 4.5%. Now this we can directly compare to that 6.6% that I mentioned earlier, and it is larger than the standard model prediction by about 2.2 sigma. Now, okay, you're going to say, well, 2 sigma, 2 sigma happens, right? So that's enough to make us curious and make us look into this in a little bit more detail. So before we get into the details of how we're going to try and suss out what is going on here, let's think about what could cause an excess asymmetry like this. Well, it could be that our standard model calculations are not yet adequate. That's always a possibility. As I mentioned earlier, there is a next to next to leading order calculation that is ongoing right now, including next to leading logarithmic resummation. That's work by Chacon and Mitov. There's also a suggestion from Stan Brodsky that the scale of the calculation will strongly impact your asymmetry. Of course, it also strongly impacts other distributions, but perhaps there's a scale setting schema that you can use to protect other distributions and fix the asymmetry. And then there's also an idea from Stainsweber and Winter that if you properly account for soft radiation and color coherence effects in your calculation, that perhaps you'll get a larger asymmetry as well. Okay, so that's ways that that's ideas that people have had to modify the standard model calculation to improve it. There's also the possibility that maybe it could be new physics. And so there are a whole wealth of new physics proposals that have been put forward to explain this asymmetry, but they fall into two very broad classes. So there are S-channel models that have some new heavy axial vector, like, say, an axigluon, and this produces the asymmetry via an interference between the parity odd scattering from the axial vector and the parity even scattering from the real vector gluon. And then you can also have T-channel models where you have some flavor-changing particle that is exchanged into the T-channel. So you get your light quarks in the initial state, they're flavor changed into top and anti-top in the final state, and the top and the anti-top wind up in the forward Rutherford peak. And and so this gives you an asymmetry. So for any of these models, for an appropriate choice of model parameters, you can get the same inclusive AFB as we see in the data. But there are differences in how the asymmetry depends on various kinematics of the event. Okay, so now that we know that there may be these different dependencies, we can study them. So we can look at the dependence of the asymmetry on the mass of the top pair and on the absolute value of the rapidity difference. So on the top plot we have the dependence on the mass, and the bottom plot the absolute value of the rapidity difference. And you can see in both cases that the asymmetry starts very close to 0 at either threshold in the case of mass or at 0 in the case of the rapidity difference, and then it rises quite steadily as these variables go up. And in fact, it looks very nicely linear. So one of the things that we can do to characterize this is we can fit a line to it, and we can also fit a line to the predictions, and we can compare the slopes. Very easy. And when we do that just as a simple measure of the significance of the result, we see that this is kind of about a little more than 2 sigma. As I said, this is a prediction of both the NLO standard model, which you can see here, and of various new physics models depending on your choice of parameters and things like this. So hopefully this will provide some new information to theorists who are looking to understand what kind of proposals might explain this asymmetry. Now, there's another variable that we can study the dependence on, and that is the transverse momentum of the top pair. So when we look at this now, the transverse momentum of the top pair is actually very sensitive to soft QCD effects, things like the details of your parton shower model, your underlying event, the color coherence and radiation, that sort of thing. And so the first thing that we want to check is whether or not we in fact get the spectrum of top pair PT correct. And we really kind of do. It's pretty good. So we have some confidence in our reconstruction and in our Monte Carlo simulations. But you know, it's not perfect, of course. So, and of course, as I mentioned, we have this Staines, Weber, and Winter calculation that produces an asymmetry from color coherence in the parton shower. And this will, of course, affect the dependence on the top pair PT as well as affecting the top pair PT spectrum. And so here we have the, now this is not corrected at the parton level, but we have the asymmetry as a function of the top pair PT, and we have this compared to fully simulated leading order Pythia Monte Carlo and next to leading order PowerPack Monte Carlo. So the shape of this dependence qualitatively resembles the standard model predictions, although there is an excess asymmetry. So if we modify these by shifting these two lines upwards to have the same inclusive asymmetry, then they're actually not very bad descriptions of the data. So this tends to suggest, although it's not absolutely conclusive, of course, but it tends to suggest that we do understand the color coherence and soft QCD effects fairly well. Okay, now that's all about the initial CDF lepton plus jets analysis. Let's look at a couple of other analyses. There's the CDF analysis in the dilepton final state, where you require 2 leptons, the momentum imbalance for the 2 neutrinos, 2 jets. Now this is actually done using only half of the CDF data set. The extension to the full data set is ongoing, but as it stands, the analysis is done with a very similar sort of chi-squared base reconstruction, a parton level unfold, and at the parton level, we see a very large asymmetry of nearly 42%, albeit with a large uncertainty of almost 16%. So this is kind of consistent with the result we got in lepton plus jets. Now how about our friends around the Tevatron, D0? They have an analysis in lepton plus jets. It also uses about half the D0 data set, a very similar analysis to the CDF analysis, and at the parton level they see an asymmetry of almost 20%. So this is really starting to paint a very coherent sort of picture now. And in fact, we can put all 3 of these results on a plot. We can even do a very preliminary sort of combination. This is not a formal combination accounting for all correlations and systematics and everything, although these analyses are all statistics limited, so we don't expect large correlations. But when we combine them all together, we get an asymmetry of almost 19% with an uncertainty less than 4%, and you can compare this to the next leading order prediction down here. So we do seem to be sitting a decent distance away from what the standard model will tell us that the asymmetry should be.
But again, if the next to next leading order is actually very different from the leading order.
That's true. There are some papers by George Sturman that suggest that the next to leading order corrections should not be large, but you can never know until you've done it. So it's a good point, a very good point, and we who are working on these analyses are waiting with bated breath to see what comes out of Chakalomitov's work. Okay, so now that's the story at the Tevatron. How about the LHC? You know, the Tevatron, that's old junk, right? The new stuff is all at the LHC. So at the LHC, though, you have a very different sort of situation. You can't measure the forward-backward asymmetry because you have a symmetric initial state, proton-proton instead of proton-antiproton. So instead, there's another quantity that is related that you can use called A sub c, the charge asymmetry. And this uses the difference in the absolute value of the rapidity instead of the difference in the rapidity. So this is kind of a central forward asymmetry instead of a forward-backward asymmetry. And the reason for this is that in the proton or the antiproton, the valence quarks, which in the proton are matter quarks and not antimatter quarks, carry most of the momentum. And so if your whole TT bar system is going this way very fast, then you know that probably you had a valence quark on this side, and if you had a valence quark on this side, you probably had an antiquark from the C on this side. And conversely, if your system is going this way very fast, it's at the opposite. And so that's what causes this shape instead of this one. Now, this is a much smaller effect. In fact, it's expected via some very generic, simple arguments, to be only about 10% of the forward-backward asymmetry in a very model-independent way. So this is a small effect, and it may be difficult to look for. So Atlas and CMS have both done measurements of this. So you can see the CMS result here at 8 TeV with almost 20 inverse femtobarns, and then an earlier Atlas result at 7 TeV with 1 inverse femtobarn. And I'm showing, well, they do this, they do the measurement inclusively, and they also do it as a function of kinematics, much like we do at CDF. And here we have the dependence on the TT bar mass. You can see that the measurement is actually consistent with zero asymmetry. It's consistent with the standard model prediction for the asymmetry. And it's actually consistent with the kind of predictions for for new physics that you would get for given the Tevatron asymmetry. So this is clearly a very difficult measurement to do at the LHC, and the sensitivity is just not quite there yet. There's some very good and very smart, very hardworking people working on this, and the sensitivity will get there, but it's not there yet. Okay, so since we don't have enough information yet from the LHC, we go back to the Tevatron and we say, okay, what can we do to get as much information about this phenomenon as we possibly can out of the 10 inverse femtobars that we've got? So one of the things that we can do once we start thinking about this, we realize that the top asymmetry is actually a very simple kind of statement. It's a statement about the distribution of the production angle, which is the angle between the top 4 momentum and the direction of the incoming proton 4 momentum as measured in the TT bar rest frame. So this angle, the production angle, we'll study the cosine of that angle. So the asymmetry is just a 2-bin measurement of this differential cross-section. You have 1 bin forward, and you have 1 bin backward. Why only 2 bins? Why not go to more? So there may be a lot more information in the entire differential cross-section, and in particular, we would like to know what components of the shape of this differential cross-section actually produce the asymmetry. And there's a very good reason for doing this, because it's different in different models. So at leading order in the standard model, you predict something that looks roughly like 1 plus the square of the cosine of the angle. And this should be a familiar sort of distribution from E plus E minus to mu plus mu minus. It's just from conservation of angular momentum. Now once you go to next to leading order, of course you get lots of additional terms that add some complications, and there's not a simple formula that I can just put on a slide. It's a couple of pages long. But you can see here's the leading order standard model, and here's the next to leading order standard model in blue. And you can see that it has some asymmetry, and it's not just a simple shift on the left and right. It has some additional shape to it. And this shape here is actually from a calculation by Bernreiter and C that includes both QCD and electroweak effects at full next to leading order. So it's very nice and very complete at the order that it's at. Now what about the new physics models? So the S-channel models generically predict an additional term in the differential cross-section. Now, this is at leading order, so we should compare it directly to the leading order standard model. There's an additional term that is proportional to cos theta, linear in cos theta, in fact. And so that is this curve here, which has more asymmetry, at least given these model parameters, than the next to leading order standard model. And it's just a line added to the parabola. Very simple. Now the T-channel models, like the flavor changing Z prime, instead add a term that looks like S hat over T hat. And this In cos theta, it goes like 1 over 1 minus cos theta, which of course diverges as cos theta gets close to 1. Now in the real models, there's some regularizing terms. It doesn't actually diverge, but it gets pretty large. And so the asymmetry here is generated by this huge pileup in the very forward direction. So these are all very different sorts of shapes. And if we study this, we may be able to discriminate among them. Okay, now we know what we want to study and why we want to study it. How are we actually going to do it? So we need some way to characterize these shapes. Well, it turns out nature is very kind and gave us the Legendre polynomials. The Legendre polynomials are orthonormal over this domain, and the use of them in studying a differential cross-section is extremely well motivated from quantum mechanics via angular momentum considerations. And so what we're going to do is decompose the differential cross-section into the Legendre polynomials, and our measurement is going to be the coefficients that multiply each polynomial in the differential cross-section. So a few things about these polynomials. The zeroth polynomial is flat. It's the only one that has a non-zero integral, and so it carries all of the information and only information about the total cross-section. Now we're not interested in the total cross-section here, so we're going to scale all of the moments we measure so that the zeroth moment is 1. Okay, and then the even degree moments are all even degree polynomials with no odd terms, so they only carry information about the symmetric part of the shape and nothing about the asymmetry at all. So that's actually something very interesting that this measurement is going to tell us that the asymmetry measurements tell us nothing about. It's the symmetric shape. Okay, and then the odd moments, 1, 3, 5, etc., these are anti-symmetric, and so they carry all of the information that there is about the asymmetry. And in particular, the first polynomial is linear, which I'll remind you that the S-channel models predict an excess linear term, so that could be one to watch. Okay, so now let's look at these different models in the basis of Legendre moments. So the leading order standard model, as we expect, because it's constant and quadratic, has a second moment, as expected. Now, interestingly, it also has a fourth moment and a sixth moment, and that's because I lied to you. It's not just 1 plus cos squared theta, because there is another diagram other than the pure S-channel diagram. There's a gluon to TT bar that has the top line of the T-channel. That's what gives you these fourth and sixth and eighth, etc. moments. But they're small, and they're pretty well understood. Okay, now once you go to the next leading order standard model, now we have a non-zero first moment, and in fact all of the moments, even in odd, are slightly larger than they are in the leading order standard model.
So this gluon is coming in the your new model, that actually gluon is, or it's...
No, that's in the standard
it's in
model.
the standard.
I just oversimplified by ignoring it previously. But it is in our Monte Carlo, and you can see it right there.
So wouldn't it kind of push the shapes together, that gluon contributed? Like
Yeah. Because it's perfectly symmetric.
So
And that's
so
why
that
we...
contribution is not that big.
No. The gluon fraction is only about 15% at the Tevatron.
So but
And-
LHC is large, so that's...
Yes, it's very large at the
So
LHC.
that's the flooding.
And that's part of what makes it so difficult to measure at the LHC. Okay, so now if we go to our new physics models, the leading order S channel, which again we should compare with the leading order standard model, it looks almost just like the leading order standard model, with the exception of this big first moment that we don't have in the standard model, but we do have in the S channel models. And then the leading order T channel looks way different from everything else. It has very large moments everywhere. Okay, so now let's start looking at the actual data. Here's the distribution, a binned distribution of cos theta in our detector, in our data. Now, we can actually, of course, what we want is we want the moments of this distribution. And if we make a binned histogram like this, then we actually discard a lot of information. So we found a way to extract the moments without doing a binning. And once we do that, we get this distribution of moments. Now, as before, this is at detector level. There's all kinds of nasty effects that we have to correct for before this plot would really mean anything. So once again, we're going to subtract from our backgrounds. We're going to generate a response matrix and invert it. And actually, there's a wonderful thing when you're doing this in the Legendre moment spaces, which is that response matrix is now no longer close to singular. So we don't need any kind of a regularization term. Makes things much simpler and more robust. Okay, so now once we've done all that correction, here's what we get. Now we're measuring the first 8 Legendre moments because that's about all that we have the experimental sensitivity to do. There's only 4 shown in this plot, but there's 8 in the table. We have pretty good agreement with the standard model, with one exception. You can see that the benchmark Z prime model, now this may or may not represent all Z prime models, but this is one Z prime model. This one is disfavored. It doesn't really look like the data much at all. So that's kind of interesting. And then we have this excess linear term, an excess first moment in our differential cross-section. Once again, it's about a 2 sigma kind of excess. So we're really kind of living in a land of 2 sigma here, right on the edge.
So, so can I ask you one question? So Z prime model is purely also TQ bar type of.
Yes.
And so I would expect that it would give the more pronounced asymmetry. So
Yeah,
but
you have to be pretty careful in tuning the parameters in order to get asymmetries that are not way too big. So yeah, they're very neat sort of models, but they're also very difficult to work with, I understand. So
Somehow you gotta deal with the fact that the cross-section can't have messed up your analysis. And, right, because
No,
we've
so
already
I'm,
excluded a fair amount of the
No, I'm
cross-section.
normalizing the cross section.
I know.
I'm trying to
Right, the question is, how could you have a Z prime that's hidden somewhere else but be showing up here? So you play the game by adding width, you worry about the coupling.
yeah, so this particular Z prime model is from work by Young Pearson Wells in Michigan. Okay, so that's pretty much what we see. Okay, now, as I said, when we started on this, we wanted to know what components of the shape explained the asymmetry. Well, here we can do that. We can say, oh, how much of the asymmetry does the first moment produce? How much does the third, the fifth, the seventh moment produce? Of course, as I said, the even moments produce zeros. So they're all zeros on this plot. And the third, fifth, and seventh moments are all consistent with 0 and consistent with the standard model. But we have all of the asymmetry that we observe is completely explained by the excess first moment. So that's really very interesting. So you can see that on this plot where it's broken out by all 4 moments, and then on this one where I've combined the nonlinear terms, 3, 5, and 7, and left the linear term here. So you can see this is at 0, and this is a good ways away from 0, and also a decent ways away from the standard model. Okay, now, you know, I've done all this crazy stuff with Legendre polynomials and moments, and we just want a differential cross-section, right? You want to see a plot. Well, here it is. We can reform the Legendre series, and then we can make bins, and we can integrate the Legendre series across those bins and give us this kind of a picture. It's a very more traditional picture. It's easy to visualize, and the error bars are really big. They're really ugly big, you know. And we understand why they're so big. They're highly correlated, and it's because we have such large uncertainties on the higher order moments, which have a lot of oscillation, and so you change that moment by a lot, and the cross-section in each bin goes up or down by a large fraction. So now there's actually something we can do. Since we've noticed that moments 2 through 8 are all in pretty good agreement with the next leading order standard model, we can say, well, you know, we don't have all that great of a measurement of these, but what if we just assume that the standard model is right for those, and then we'll let the data tell us what the first moment is, since that's the one that seems to be interesting. So this is a little bit a posteriori, and it's definitely more model dependent than the measurement with no assumptions, but it can still be very interesting. So we introduce that assumption, including the scale uncertainties, and we combine that with our measurement using the likelihood from the covariance on the measurement. And this gives us a more precise, albeit more model-dependent estimate of all the moments. In fact, it gives us about a 10% improvement in the precision on the first moment. And so you can see the result here. You can see clearly we have an excess on this side and a deficit on this side. And if we subtract this, now this plot is a little bit artificial, of course, because we've basically constrained it to look exactly like a line. But it does look exactly like a line, so I kind of like that plot. It's very pretty. Okay, so now that's pretty much all that we've done with the angular distribution. Is there something else that we can get at? Well, it turns out that yes, there is. So I mentioned that sometimes we don't reconstruct the top and the anti-top 4 vectors correctly. Is there some way we can get around that? Well, the lepton is just a nice, clean track all by itself in our tracker. We measured that very, very well. And so we know the direction, we know the energy of that lepton, and we don't have to worry about any of this nasty TT-bar reconstruction and chi-squared stuff. And in fact, the lepton direction and the lepton asymmetry are kinematically very correlated with the top direction and hence the top asymmetry. In fact, we expect, in the absence of top polarization, we expect the lepton asymmetry to be about half of the top asymmetry. And so what we're going to do this analysis, we're going to measure the spectrum of the lepton charge times its rapidity, which you can see this here from several models at the generator level. And then we're going to correct this for detector acceptance effects. And then we're going to fit the acceptance-corrected lepton asymmetry in different bins of q times y, the charge times the rapidity, to the model and this is just a phenomenological model, it works marvelously well. We're going to fit this model to our data. And then we can use this model to extrapolate out past the ends of our detector where we don't have any leptons. And that point is marked by these dashed lines. So we only see the central part, which is the bulk of the distribution, but there's also the events that do fall out here have a very large asymmetry. So we kind of want to know what's going on out there. Okay, so here's what we see in the data. This is the distribution of interest. And once again, you can see the points on the right are high, the points on the left are low. There's the asymmetry, you can already see it. And in fact, this is almost the same analysis as the other lepton plus jets analyses that I've shown, except that we've loosened one of the jet ET cuts to get additional acceptance. This wound up being a nice innovation that we had. And so then we subtract the backgrounds from the data, we calculate the symmetry, you see that here, and then we correct it for acceptance, and that's these points, which are only very, very slightly different, and we fit it to our model. And from that model, we can extract the inclusive lepton asymmetry, and we get 9.4%. With an uncertainty of about 3%. And this is in comparison to the next leading order standard model, which is less than 3%. So this exceeds the prediction from the standard model by, again, a little bit more than 2 sigma. But interestingly, it is very consistent with the expectation of what we would get given the observed TT bar asymmetry, which would be about 7.6%. So we're very close to that, which is really quite nice. Okay, and then in the dilepton channel at CDF, once again, we also have a measurement of the leptonic asymmetry there. This one actually uses the entire CDF data set. It's really quite a nice analysis. It uses the same methodology, and it measures an asymmetry, a leptonic asymmetry of 7.2% with a fairly large uncertainty of 6%. So this is, it's kind of right on the edge of consistent with the standard model. The standard model is a little bit inside the 1 sigma band. But we can take these two analyses, the lepton plus jets and the dilepton, and we can combine them. Now this is a real formal combination with all the correlations taken into account. And we get 9 with an uncertainty on the high side of 2.8 and on the low side of 2.6%. Now, okay, once again, what about D0? D0 also measures the lepton asymmetry in both lepton plus jets and in dileptons using their full data set. They do correct the parton level, but unlike the CDF analyses, they don't extrapolate to the entire leptonic phase space. They use a restricted eta range, or restricted pseudo-rapidity range for the lepton. And so this means that they can't be directly compared to CDF or directly compared to full phase space theory calculations. One could do a restricted phase space theory calculation, but I don't know of any that have been done that way. But here's the results that they get in the lepton plus jets channel. They see 4.7%, and in the dilepton channel, they see 4.4%. So these are lower, but once again, they're in a restricted phase space, and we expect this to come up somewhat, at least, when we go to the full phase space. And work on a Tevatron combined, both CDF analyses and both D0 analyses, work on that combination is proceeding.
Yeah,
So-
the lepton plus jet should come up a fair amount. I think the dilepton,
May come
they
up
have
less.
both.
Mhm.
They have both results, and I don't remember which one this is.
Right.
But it's only 10%.
Yeah, yeah. So,
But the lepton plus jet should come up a fair amount, I think 30%.
yeah. So that will be quite nice when we have that combination going. Okay, so now let's try to bring things to a close. What explanations survive? We've done a lot of very interesting sorts of tests of this phenomenon, and it turns out that most of the T-channel models tend to be disfavored, whether by the Tevatron analyses or by the LHC analyses, although this plot predates the newer CMS result that I showed a few slides back. The S-channel models, if you make the oxygluon low mass and you just make a simple model, then that's already excluded, not by these asymmetry results, in fact, but by resonance searches in dijets and ditops, both at the Tevatron and the LHC. So you have two options for the S-channel models. You can put the oxygluon way, way high in mass, put it above the reach of the LHC resonance searches. And that's very easy to do, it works quite well. Or you can put it down at low mass, but make it very broad, make it too broad to see. Now this gets a little fishy because in order to make it so broad, you have to add additional particles for it to decay to, and well, why haven't we seen those particles? But maybe, you never know. Or of course, I want to keep emphasizing that improved standard model calculations via a number of different avenues may take care of this asymmetry. So let me just sum up. We do see an anomalously large forward-backward asymmetry in top pair production at both CDF and at D0. The asymmetry grows with the TT bar mass, and it grows with the TT bar rapidity difference. When we look at only the leptons, we do see a compatible asymmetry. When we measure the moments of this angular differential cross-section, we see an anomalously large linear term, and that anomalously large linear term does in fact dominate the observed forward-backward asymmetry. The new and improved standard model calculations, or else very heavy or very broad axigluons, do remain as viable explanations. And now you're probably wanting to ask, well, what do we do next? Well, we should use the full data set for the D0 top asymmetry measurements. We should use the full data set for the CDF dilepton top asymmetry measurement. I mean, I know that work is ongoing, actually by Dave and a student here at Texas A&M. We should actually measure the top quark polarization, because some of these models predict a non-zero polarization. And that would be a real smoking gun for new physics. We can wait for theoretical development. Whether it's new physics models, maybe somebody will come up with just the most brilliant model that perfectly explains everything, or maybe we'll just get better standard model calculations. And we can just wait for more data from the LHC and better precision. So thank you very much.
Yes, I got a little bit lost on the extrapolation of the lepton. We were going towards high forward regions. Can you explain that again, please?
So we observed that in lots of different models, whether standard model at different orders or new physics models, we see the same kind of a shape here in this distribution. And these shapes are all the same, just with a mean shift. And when you calculate the asymmetry, all of the models are actually really a very good fit to this functional form. And so you can take only the lepton acceptance that's below 1.25 in rapidity, and you can fit the parameters of the model, the parameter, there's only one parameter, to the data, and then you've totally parameterized your model, and then you just know, because you know it has this shape. Well, you think it has this shape, you don't know because you can't see it. But
I think I got it. You just do that just to be able to compare the number you get after deconvoluting all the effects of the detector to a theoretician's number.
Exactly. Thanks. Any other questions?
How much integrated luminosity did the LHC require before having some useful sensitivity?
It's hard to say. Go back to these slides. So this is with the whole ATV. Well, I guess it's not quite the whole ATV data set. It's pretty close, right? And so
That's all.
yeah, this is from September.
That's 19.7. That's all.
Yeah, after.
Oh, that's sorry, that's
all.
all. Yeah, okay, that's all of the ATP. So you can see that the difference between the standard model predictions and these two new physics models, which are actually those two new physics models will generate significantly larger asymmetries at the Tevatron than we see. So if you bring these down somewhat, then they're well within the 1 sigma band of the data. If you get twice the precision on this highest mass point, then maybe you can start to see the difference between the axigluon models that match the Tevatron and the standard model. So that's 4 times as much data, and that's where you just begin to start to see it. So it's going to take a lot more integrated luminosity. Or maybe somebody will come up with a really brilliant analysis technique or a different observable. You know, I don't want to sell all those smart people short.
Do you know if those error bars, I mean, there are 2 error bars on each. Is that the 1 sigma, 2 sigma, or is that statistical and systematic?
I think it must be statistical and systematic because they don't scale. They're not the same size on 2 of the 3 points. But I can't tell you which one is which. I don't know.
So if you say you're going to get our square root of 2 for each doubling of the data, it looks like you're going to need a factor of 4 or factor of 8 in sensitivity. So it looks like you might need somewhere like 60 times more data. What?
At the same energy.
Yeah, you could have a higher.
Yeah, if you go to higher energy, the higher cross sections.
Yeah, you'll get higher cross
Pile up
sections.
is also
Yeah,
gonna hurt
that's
you.
right. Yeah,
So-
you'll pile up.
And-
But
and
that
also
shouldn't
the
make that much
gluon
of a difference
fraction.
in your identification.
When you go to higher energies, the gluon initiated fraction is going to keep going up.
Oh, yeah, so you're
So that's
going to
gonna
wash
continue
out your
virtue as well.
asymmetry.
So it's really unfortunate that this is so difficult, or said another way, it's unfortunate that the LHC is a proton-proton collider. But, you
So
know.
what's the axis-gluon mass? What's the
So this one is 1 TeV, and this one is 1 TeV and 1.5 TeV. Although, if I understand correctly, these are not models where you just stick an axigluon into MatGraph. They're some effective field theory models. So I'm not certain that they actually have a resonance. So, but for comparison, the axigluon model that we use at CDF, this leading order S-channel, this is a 2 TeV axigluon, and that provides an extremely good, I mean, it's amazingly good match to our data. We actually tuned the parameters of this model back when we had, I want to say about a third of the CDF data set, and it has continued to be an astoundingly good match for the
So
CDF
14
data.
TeV LHC won't be not too big.
It will be difficult.
Okay, with 14 TeV.
Yeah, at 14 TeV you may be able to just see the resonance. Although you can continue to run the axigluon mass up and increase the couplings. Now, increasing the couplings, that's not that well motivated, but you can get rid of the resonance by sending it higher and higher while keeping the asymmetry. So, or of course you can just make it really broad and low mass. You can even put it below the TT-bar threshold. And actually, that's one of the interesting things. If you keep the resonance above the TT-bar threshold, make it broad so we can't see it, then somewhere maybe, say, 600 GeV, there's a pole, and below the pole the asymmetry will have one sign, and above the pole the asymmetry will have a different sign. So that would really be an interesting signature to see. That's going to take, again, a whole lot more data to get that fine of mass resolution, but if you can see it, then that'd be nice.
You see with the Z and the W is very useful.
Yeah,
You know,
basically
do
looks
they
just
have
like
the next to next
asymmetry.
leading order for the Z's? Because I know we've got plenty of statistics. Are they just still doing NLO?
I'm not sure. I have to ask Willis.
Yeah, because he would at least be able to answer the question, what's the ratio of next to next to leading order to leading order? I mean, it's colored versus electroweak production,
Yeah,
so it's.
That would be for next to next to leading order for the axigluon type things. And what we're interested in is the next to next to leading order just in vanilla QCD.
Right.
And that's just much uglier.
Yeah, but right, it's.
You just want to make sure that whatever leading order you're using is already stable. Further iterations will not change the cross-section much.
Well, we know that we get the cross sections about right.
But we're not changing, sorry.
Yeah, but the asymmetry.
Yeah.
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 So.
Yeah. Well, and it's worth pointing out that because the asymmetry at leading order is 0, the asymmetry calculated at next to leading order is really a leading order effect.
That's right.
Alpha to the 4, this is leading order for the asymmetry. So we only have a leading order calculation for the asymmetry. So there's some discussion among theorists about what you should put in the numerator and what you should put in the denominator because of this fact.
Although there's a differential asymmetry even at leading order.
Yes.
The total asymmetry is 0,
Yeah.
but it's an asymmetry, like for example, as a function of PT.
Yeah, so right here. So this
Yeah.
curve here is a leading order Monte Carlo Pythia, and it has an asymmetry. And if you integrate this up, then you get 0. But it's non-zero as a function, which is kind of interesting, really.
So more or less the ZPEG model is gone, just the axigluon model is surviving because of the.
I hesitate to say that it's gone, because if I say that, somebody's going to jump on me. There's a lot of clever people who are working hard on Z-prime models and are very
But
attached
you
to
need
them.
a little bit low mass Z-prime, so that's the.
You typically need a fairly low mass
And
Z-prime.
there is a good constraint, like also from left.
Yeah,
Like,
so you make it leptophobic,
Yeah, I know. So
and you make it not
dodging
coupled to
all
charm,
those-
so you don't have to worry about flavor changing neutral currents. Although even then, you still have to worry about atomic parity violation, which hurts it pretty badly. So. But I know some folks at, for instance, Cincinnati who really get mad at me if I told them that their Z-prime models were dead. So I'm not going to say that.
So about the times, so you said running over the full data set. Are there any specifics in the improvement of the analysis? What features there?
We have about this 16% uncertainty here. So just from statistical power, you can expect that this will go down by a factor or two. The analysis technique should be somewhat improved. The acceptance should be somewhat larger because we've had new developments in dilepton top analyses in the intervening time. So I think that we'll see improvements above luminosity, but I wouldn't expect them to be overwhelming or dramatic. It should be noticeable but incremental, is my guess.
Other questions for John? If not, let's thank him again.